The math over here, and this is the 2021 AMC 12B problem 23. Here's a view of this problem. 3 balls are randomly and independently tossed into bins numbered with the positive integers so that for each ball, the probability that it is tossed into bin I is 2 to the negative I, for I equals 1, 2, 3. In other words, every single positive integer. More than one ball is allowed in each bin. The probability that the balls end up evenly spaced in distinct bins is P over Q. And we want to find P over Q, where P over Q is a maximum as not irreducible any further. Okay, and then we have an example over here. If it's in 3, 7, 17, and 10, the balls are placed in that order, then we do in fact have that they are evenly spaced. Or in other words, if the spacing forms an arithmetic progression, then it is valid. Okay, so first let me just get a visualization of this problem. So bin 1, call this bin 1, call this bin 2, bin 3, and so on. So we want to find the probability that we get evenly spaced. Well, suppose we throw a ball into bin 1. Then how can we construct this such that they are evenly spaced? Well, we can throw the ball into bin 2, and then we must throw the ball into bin 3. Or what we could do is we could throw into bin 1, and then we could go to bin 3, and then we must throw it into bin 5. And then I'll do one more before we generalize. Or we could throw it, and then 1 by 2 cubed. We could throw it into the 4th bin, and then into the 7th bin, and then so on. So let's try to generalize this now. So we have a 1/2 in every single term. So we can write this as summation k equals maybe 1 to infinity, or 1 by 2 raised to the power 1. And then how do we go to the second term? Well, all we're doing is we're adding the 1 and then plus the k. And then to get to the third term, what we're doing is we're adding k to this thing. So 1 plus k plus k. Or in other words, 1 plus 2 raised to the power 2, 1 plus 2k. Right? And then plug in some values of k and we can see it works. For example, 1, 2, 3, and then 1, 3, 5, and then 1, 4, 7, and so on. So let's maybe make this a little bit more compact. K equals 1 to infinity, and then we can write this as 1. Using exponent properties, we add the exponents to get 2 plus k, 3 plus 3k. So 2 raised to the power 3 plus 3k. Okay, awesome. So let me just call this case 1. So let's go on to case 2, and then we can generalize even further what this problem is really asking. So if we drop a ball into bin 2, we get 1 by 2 squared, and we can also drop it into 3 and 4. We could also go and do 2 squared. We could also go 4, and then we must drop it in 6, and then etc. Okay, so now generalizing this, we get summation. This is actually very similar, and then we can easily make a general argument from this. We'll have always a 1 by 2 squared term, and then all we're doing again is we're just adding a k. 2 plus k, and then we're adding a k again, so 2 plus k or 2 plus 2k. And then again, making this more compact, we get summation k equals 1 to infinity of 1 over 4, 6, 6 plus 3k, 2, 6 plus 3k. And now we can make a general argument. If we put it into 3, then we'll have summation of 1 by 2 cubed, and then we'll have to add k, so 3 plus k, and then we'll have to add the k again, so 3 plus 2k. And adding will give us 9 plus 3k, and so on. So we actually see the sum of the probabilities will be summation k equals 1 to infinity of 1 by 2 raised to the power 3 plus 3k plus summation k equals 1 to infinity of summation 1 by 2 raised to the power 6 plus 3k, and then so on. So I think this is going to be the first video ever where we have to move on to another slide. So let's just note this, okay, and then maybe we can expand this out a little. So this can be written as 1 by 2 raised to the power 6, the first summation at least, 2 to 9, 1 by 2 raised to the power 12, etc. And then we need to add to this. Well, if we go back, if you don't remember it, we can go back. And then we start at k equals 1, so 2 to the 9th. and then 2 to a 12th, so on, because we're just doing 3k again, so on, right? And then we see we're summing geometric series. Okay, so let's apply formula to infinite geometric series formula to each of one of these. So 1 by 2 raised to the power 6, and this becomes 1 minus 1 by 2 cubed. Adding it to this will give us 1 by 2 raised to the power 9 by 1 minus 1 by 2 cubed. And now we see whether this is going on and on. We'll just have a 1 by 2 to the 12th over 1 minus 1 by 2 cubed for the next term. So we have, we could sum the numerators using an infinite geometric series. That gives us 1 by 2 raised to the power 6 by 1 minus 1 by 2 cubed. And we have to, and since we're adding everything, the common denominator is 1 minus 1 by 2 cubed. And then now we just are left to evaluate this. So 1 by 2 to 6 is 1 by 64. And then 1 minus 1 by 2 cubed is 1 minus 1/8, which is 7/8. We're squaring that to get 49 by 64. So multiplying by the reciprocal will give us 64 by 49. This is equal to 1 by 49. And then if we go to our answer choices, we'll see that P plus Q will have to equal 50. But there's no 50 in this answer choice. And the reason is that they can be thrown in any order, right? And this just accounts for one order. So we have to multiply this by 3 factorial to account for the arrangement of the balls. This gives us 6 over 49, sum to give us 55, and that is precisely A, and we are done.